Hello everyone. So today I will try to present some information about big data tools. So for the record, this is the first time I'm doing this live, so I will do my best for this session to go well. Also, we will try to offer you the possibility to actually test some things. So as you can see, the course is provided through notebooks, through a Jupyter notebook, and we created a cluster on which you will be able to access, load those on the Indigo website, so that you can actually interact with the Hadoop cluster that was deployed for the occasion. So a quick introduction. So basically, high-performance computing and big data used to be distinct discipline with little or no overlap. But technically, this is not really anymore the case. So many researchers are moving the workload from HPC to big data, while some big data workloads are being ported to HPC. So you have kind of some movements. The big data workflows being quite different from traditional HPC ones. These HPC infrastructures are in general quite difficult to run big data jobs on them. And for instance, the main aspect is maybe the object storage that's not always available and that has a specific behavior, which is also easier to connect with, let's say, for instance, Hdfs than other traditional file systems. In this session, I will try to present broadly some of the tools, the most basic ones, the most well-known ones in the area. So we will see a few technologies like Hdfs, MapReduce, Yarn, Spark, Kafka, and also Spark streaming. But first, maybe a quick return on the big data survey. So in fact, some time ago, we tried to ask some questions to the community of the SESI users to actually measure their interest in such structure, so a big data infrastructure. And well, to summarize basically what came out of this survey, you can find here a few bullet points. So 95% of the participants manifested an interest towards those technologies. The kinds of information they wanted to manipulate was quite large. The spectrum was quite broad, so it was either image, just data files, or whatever, many different things. The interest was mainly targeted to Hadoop, so the combination of Hdfs and MapReduce 2. Spark, Hive, Cassandra, Impala, Elasticsearch, Solar, or even other technologies that are not listed here. Also, we realized that most of the workloads that were actually described were relying on Python, using a lot of libraries, and most of the time bleeding edge ones. So basically the latest version that could be available anywhere would be preferred over the previous one. 70% of the participants also manifested interest in Jupyter or Zeppelin, so basically notebooks like this one. There was also a request for the RStack or RStudio even though it was only covering 38% of the persons that were requesting R. And also 45% of the persons that answered the survey wanted to be able to actually do benchmarks, so to have some kind of reproducibility in all the results, which is sometimes quite difficult to achieve on a Hadoop infrastructure. So considering this survey, considering the results, we wanted to try and answer those needs. And the result was, in fact, the infrastructure we call the HPDA, which was last year in its version 1. So this year we are almost inaugurating the version 2. So what is this? Well, technically this is a platform that can be considered between virtualization and a cloud solution, and it's targeted at high performance data analysis. Okay, so the point is to try to bring those workloads closer to HPC and HTC to try and reach convergence with big data workloads. So the version 1 was fully built with decommissioned hardware from HPC clusters. But in version 2, everything is brand new. So the version 2 is based on ROM processors exclusively and provides many tiers in terms of storage to try and get the best possible performance with support and everything. So the current implementation actually runs all the workload inside KVMs. But we are also evaluating the possibility of actually using container-based solution. So either directly or through Kubernetes or OpenShift maybe, but Kubernetes would be preferred. But for the moment, it's fully KVM. So the current status, so basically the specification of the infrastructure you will be able to use today is a bit limited in terms of resources because it's still in beta. What happened is that we just ported the version 1 of the KVMs on the version 2 infrastructure. So we have 36 vCores inside the infrastructure that manages Hadoop and 90 gigs of memory available for jobs. However, since we are in version 2, technically all the hardware and software stack are finalized, so we are almost ready to go. So the HPDA v2 should be available broadly in the first quarter of 2021, at least we hope. It should come with a big increase in terms of available vCores and available memory. We also plan to bring some GPUs, but this will be for a later step, as well, 2020 was kind of a difficult year to actually buy new equipment, so we needed to push this a bit later on in our agenda. So basically, did we actually answer your requests? Yes, so the stack that you will be able to use today actually includes all the technologies that were mentioned at some point in the survey, or at least almost every single one of them. So the only one that is left out for the moment is R, which will be available in the V2. So you have basically Hadoop, Yarn, Spark, Solar, Cassandra, Elasticsearch, Hive, Impala, Kafka, and some more. I'm not listing all the different libraries attached to those things that are actually present, but there is a ton of them. Also, Anaconda 3 is available with all sorts of libraries, and it's possible to install others upon request. And clearly, as you can see, notebooks are being part of the party. So the course of today will be later made available as documentation for using the HPDA, and some other notebooks will be created to actually cover the other softwares that could be installed, like for instance, Elasticsearch, Cassandra, so that you can have some examples on how to use those systems. So this course will cover really the most basic elements of an Hadoop infrastructure. So we will have an introduction to Hdfs, so the object storage used in this platform, MapReduce using Python streaming, and also a Java example for the ones interested. We will see a bit of Spark as well as all its operators that you will be able to test by yourselves, an introduction to Kafka, and as well as Spark streaming. So as you can see in the picture below, you have basically a quick representation of the stack and how the different components are actually linked together. So down here you have Hadoop with Hdfs, because technically Hadoop is the combination of multiple technologies, so basically Hdfs and Yarn. So at the bottom layer you have Hdfs, which is the object storage. On the side you see you have Zookeeper, which is basically keeping track of all the configuration of the different systems, including Hdfs, Yarn, and the others. Then over Hdfs you have Yarn, which is actually the scheduler used in the Hadoop environment. On the right, you see Cassandra, which is at the same level as Hadoop. It's just because Cassandra actually can be installed next to it, but it's not actually storing data itself on Hdfs. HBase, which is just here on the left, relies on Hdfs. And you see the pile actually being built this way. So over Yarn, you will find Spark, the MapReduce paradigm, and then other systems that can be installed. So Storm, Solar, Mode, Hive, and so on. So this is it for the just the introduction. So do not hesitate if you have any questions. I will try to answer them the best I can. So now I will ask you to ask directly in the chat for receiving an access. So you will be provided a combination of a login and a password that will allow you to connect to this system. So I will publish the actual link to use. Please be aware that this is indeed an HTTPS URL, but it's using a forged certificate, so you will have to actually accept this certificate to go forward. So going to this website and using the credentials that will be provided to you, so I recall, ask for them in the chat, you will be able to access this and upload the files that were found on the Indico website. The files on the Indico website are exactly the ones that I'm currently presenting. You just really have to upload them on the system and start using them. So the first part of the session will be about Hdfs, but I will probably leave you a few minutes so that you can actually take the time for connecting yourself to this structure and actually load the notebook before going forward. In the meantime, I will maybe explain a bit more about those access. So for the previous year, we actually created also accounts like those, and we made them available for the duration of the session, as well as for the multiple weeks after the session. I'm sorry, but this time we won't be able to maintain that for such a long time because we are in the middle of the conversion of this infrastructure to the new V2 model, and especially for the accounts. So the accounts will be handled in a different way, and we will have to scrap the current setup in this respect to actually. I see only one connection right now, another one. Okay, it's coming. If at some point you receive an error during the connection, please just notify us through the chat. That could happen if too many connections occur at the same time. Okay, I see a few more connections. So once you are connected, I recall, just go on the Indico website, download the notebooks, go back to the URL that I provided. Once connected, just upload every single file that was provided. Yeah, so the mention of the insecure website is due to the fact that we forged the certificate SSL. So I remember you, this is just still the version 1 running on V2 platform. It's not yet fully converted, so this message is normal. The certificate is ours, it's fine, you can go forward. So I just see a couple of users connected. So 4 of them, I think. So if others are interested, just request a pair of password and login on the chat. You will receive them as soon as possible. I observed that many of you seem to try to connect with their login. You need to ask for one. All the logins are CC 100 something with a password that will be provided if you ask them. So do not hesitate to ask for the credentials. I will go forward with the presentation for now. So we'll start with Hdfs. So which is the object storage. So there are multiple Hdfs commands that roughly corresponds to the one that are available on any Unix system. And during this session, we will just show you how to use them through a Jupyter Hub notebook. So however, keep in mind that all those commands are available when used directly through a terminal. It works the same way. The notebook only interprets those and executes them as an SH script. Also, do not forget, even though the provided commands do resemble the ones of any Unix file system, Hdfs is not a file system. So all records that are written on Hdfs are in fact immutable. And this is due to the fact that Hdfs does not support random writes. Okay, so even though it's not possible to actually modify a file, you can actually extend, so append data to existing files. So here below, you have a list of multiple commands that are basically available on Hdfs. So ls, du, mv, cp, rm, put, get merge, scat, make dir. So basically all the commands that you should be familiar with using the SASE clusters or even any laptop using Unix below. However, you see also that there are some other possibilities like get merge, set rep, stat, and so on. You will see later on in this session what are those used for. However, of course, there are multiple other commands. This is really just a basic introduction. So if you are interested, it's possible to get a listing of everything that is available. So quick start. So all the commands you write preceded by the exclamation mark are interpreted as SH commands. Okay. So if we take a look at this example and execute the box, you see that the whoami command provides me the username, so you should get something like cc 100 something, and here I will get my actual home. So this is my home, this is my local home. Okay, on Hdfs you have another home, which is the Hdfs home, which is /user/your username. Okay, so the first thing you will need is to actually build the material that will be used for this session. And for this, we have a quick notebook. So you just have to execute it, and it will create anything that is not yet present so that you can proceed forward. In my case, you see that the directories were already there, but you won't have those messages. So the first command is, of course, the ls. So in the following cells, we will just take a look at the different commands you may use on Hdfs, and clearly you will see that they resemble the ones you are familiar with, but with just a small difference. So here, the first one we will try is the ls. As you can see, it's not just plain ls. You have to invoke Hadoop tell it you want to work on the file system, and provide the command you want to run. Okay, so if you make the first one and execute it, it will just first list the files, a plain list. Yeah, sorry, I have quite a lot of them. If you want to specify a path, it's as you would in any Unix system, you will just, after the ls, mention the actual path. And if you want a recursive listing of all the files included, here you will again add all the parameters, so dash, then parameter you want, and execute it. So here, for the first example, the ls, you have the listing of the files. Here, the equivalent, but with specifying the actual path. And then here, the recursive one, which is a lot more comprehensive, of course, on my session. So you have also the makedir command, and it works the same way. So it's always Hadoop fs followed by the actual command, okay? And of course, path in which you want to create the directory. So I will maybe let you a few minutes to actually go through those different commands. Hearing me and showing you all those things is not really interesting. I think it's really better for you to actually test this by yourself. You will see that the syntax is quite close. It resembles really closely the commands we use generally. I will just go directly to others that are a bit more interesting to me. So the RM. So let's say we want to remove a directory. Okay, so this one on Hdfs. As you can see, we ask Hadoop to work on the file system to remove a file, well, to remove something recursively. And here the path is user, so basically the home path on Hdfs, then the actual username, which is mine, and then a directory that was created before. So I will just make sure it's created properly. So execute the cell up. I will continue so I can reach it and come back to the RM. So here, the interesting thing here is that if you try to execute this command, you see that in fact, what you just removed is not really removed. The default policy in Hdfs is to actually move everything that you ask to remove to the trash directory. And the trash directory is located at user slash your username slash .trash. In fact, the idea is simple. It's just to provide you an additional layer of security. So usually when we use Hdfs, we store actually big files. Hdfs, the block size, the minimum block size in Hdfs is in fact parameter, well, modifiable, but the default one is 64 megabytes. So the point is that any file you will try to remove from Hdfs is supposedly quite large. So to avoid actually every single rm command moves everything to the trash. A bit like on Windows, you suppress something and it goes to the trash. Same principle. However, it's possible to override this behavior is if you are actually sure of wanting to remove completely without going to the trash something from Hdfs. And this is the skip trash argument that you will need to add to the line. Also, we are running on Hdfs. So Hdfs is technically a system that is distributed among multiple nodes. Okay. So yes, this is an object storage, but it runs in a distributed fashion. And technically, every single file that you put on Hdfs by default is replicated 3 times. So again, this parameter can be modified globally for the whole Hdfs instance, but you are also able to modify this parameter yourself directly on specific files. And for this, you have the setrep command. In fact, what you need to do is just to call setrep, specify the -r if you want the command to be executed recursively, and then specify the replication factor. So if we execute this, you see the replication set goes to 1, okay? But you also see something else. In the listing of your files, you have file 1 and file 2. You see that in the first column, you have the actual replication factor. So 3 stands for 3 replication. So basically the file will be reproduced exactly on 3 different nodes. or in this file 1 to specify that there is only a single copy on Hdfs. So if you remove file 2, or if the node on which file 2 resides gets down for whatever reason, it won't be accessible anymore. Also, there are a few commands like the get merge. So the point is, again, the same thing. On Hdfs, usually you manipulate big files. However, after some processing, using MapReduce, for instance, what we will do, in fact, in the next session, you may output quite a huge number of small or smaller files than the data you provided as input. So an interesting thing to actually be able to do is to merge those files and bring them back to your local storage, so to your local home. So as said here, a common practice while using Hdfs is to split huge files to match approximately the block size of Hdfs, which is 64 MB by default, as I said before. Thus, sometimes it may be useful to directly merge given directory in a single one when coming back to your file system. For this, actually, you use the get merge. So in the example we'll provide later on, which is basically the word count, the point is that the input file is supposed to be a book. So, okay, it's still quite small, but it's for this session to run quite smoothly. But imagine that this input file is way bigger. After the different operations that will occur during the processing, in fact, you will get out with tons of output files, tons of smaller output files. So when you want to get back the actual final result, it may be interesting to use this command to get back a single file with all the data merged into one. Then, of course, you have the chmod and chown that you will have to use, because basically when you try to execute something directly from Hdfs, the same rules apply as on any Linux file system. So if some file is not described as executable, you won't be able to execute it. So here it is. I will leave you a bit to it. You can try those different commands. And if you want to go further, do not hesitate to type Hadoop fs-help. That will provide you a listing with all the different available commands on the Hadoop file system, so on Hdfs. So I will probably leave you 10 minutes and take a quick break on my side during the time you actually test this session. Do not hesitate to ask your questions. I will go through them right now during those 10 minutes. And do not also hesitate to actually ask an account if you did not receive one yet. So yes, indeed, if you have indeed a Jupyter notebook, well, a Jupyter system or Jupyter Hub system running on your notebook, you will maybe be able to test some things or actually read the content, but you will clearly not be able to use Hdfs or anything else. This relies on the setup of this particular cluster, of course. And basically, when logging in to our URL, you land on a login node that has actually the possibility to connect to all those things. So for the question concerning the Hdfs commands in the terminal, yes, of course. So in fact, here we are just using a notebook as a means to provide a course. But technically, if you were able to connect directly to the machine through SSH, you would be able to execute those exact same commands. Like, let's say, for instance, this directly from a terminal. So I can maybe show you this quickly. So let's say here I'm on my session and I want just to have the listing of my files. You see you are able to actually do that directly. Okay, there's really no difference. The notebook is just there to facilitate this session. But in the end, on the version 2, when this will be made available to all SESI users, you will be able to log in directly through SSH on that particular machine and use all those commands directly inside the terminal. Technically, you can as well do this in Jupyter as we did not disable the terminal function, so you can open a terminal and do it. So while you test those things, I will maybe provide you just a bit more information about Hdfs and the things you can do with it and shouldn't do with it. So technically, Hdfs is a distributed system, a distributed object storage. This means that as long as the replication factor applied to it and to the files that you want to manipulate is large enough, it can sustain node loss. So if at some point one of the replica of the data goes down for whatever reason, network issue or whatever, the data will still remain available because there are still multiple replicas. Also, one of the default behavior of Hdfs that you can, of course, alter if you want to some extent, is to say, okay, the data is supposed to if during a certain amount of time, the node, well, one node dies, let's say for 1 hour, and if we specify that after 30 minutes, Hdfs must ensure that the replication factor of each file is still 3, it will try to re-replicate the data to another node to reach again the factor 3. So this can be, of course, modified, but this means that if some maintenance is planned, you need to inform Hdfs about it, because if you do not do it, it will try to re-replicate quite fast all the different files that are under-replicated at that moment. This also means that, well, this is also one of the advantages of Hdfs. We will discuss this a bit more with MapReduce in the next round. But the point is that it can support multiple critical failures of different nodes before actually failing a job or failing just data access at some point. So for this, it's quite convenient. However, concerning the things you could or shouldn't do. So Hdfs is really targeted at huge files. So never try to use it as a conventional file system. Let's say you want to put zillions of small files in it. No, that's not a good idea. You will basically overload the master node of Hdfs, because Hdfs is, yes, distributed, but all nodes do not have the same role. So you have master nodes and worker nodes. The worker nodes are actually just manipulating the data, ensuring the replication and their storage, but the master node are actually keeping track of what are the files stored and where they are. And the more files you try to add, considering the block size, the default block size is supposed to be 64 meg. If you try to insert tons of really small files, well, in fact, the minimum unit you will be able to use is 64 meg. At least it will be the reservation made. And at some point, you will start to actually overload the master node. It's really not created for this. So the default size is, again, 64 meg. You can alter it. You can get it down. You can get it up. But get it down, basically reducing this block size, should only be done by persons that actually master Hdfs and know what they are doing, because doing so, you need to actually revise the structure of the master nodes. This is really important. This also means that some workloads are not to be run on Hdfs. If you want to manipulate tons of very small text files, for instance, in this case, for those things, you should use another technology, maybe over Hdfs, but not Hdfs itself. You could maybe store those information in blobs, in HBase, so basically a database, or things like this, but not store directly the data on Hdfs. Hdfs is, again, a distributed object storage that is created to actually store huge amounts of information, so basically big files. This is maybe a quick reduction of what Hdfs can do, that is true, but nonetheless, those are kind of good practices to keep in mind to avoid having basically issues, performance loss, or issues with the master nodes handling Hdfs. So I hope that everything that you are trying now on the first notebook goes fine. Do not hesitate to ask if you have an issue at some point. We are here to try and answer all the questions you may have. I will leave you 5 more minutes, then I will start the session MapReduce. Maybe one more quick thing that could be of interest for you if you want to actually try this home without using this cluster. It is possible to do it. So it is possible to install the Hadoop stack locally, or even download VMs that actually integrate the full stack. However, keep in mind that this is suitable for small tests, but clearly the point of Hdfs, the point of the whole Hadoop ecosystem is to work in a distributed way. Those systems are eating quite a lot of RAM, so even though you will be able to do some tests, you won't be able to actually run any workload on this, or the delays in the execution of almost anything will be just enormous. So even though if those things are available online, you can find them either through Cloudera, Hortonworks, or whatever. Be aware that this is really hungry in memory, and this is really not done uploads. It's just there to make tests and only test. Okay, so we'll go to the next chapter, which is MapReduce. So this practical session will be divided in multiple parts to approach the concept of the MapReduce programming model. So it's not a programming language or whatever, it's really just another programming model. And here we will present you, explain you how this works using a really simple example, and technically the most canonical one, which is the word count. In the first part of the session, we will focus on writing this simple word count program in MapReduce, but just using Python and directly as those were plain SH scripts, not running on an Hadoop structure. Then we will show you how to make this work on MapReduce over Hdfs. Then we will show you also a quick example on how to do the exact same task, but with writing in Java. We won't take too much time on this, since the focus of those sessions is to manipulate Hadoop through Python exclusively. But for the ones interested, you will be able to take a look at the code proposed in Java. So in this schema, you see actually the workflow that is supposed to be used. So the point is that you're supposed to have a big quantity of data at some point. You will need to copy it first to Hdfs. Then two operations will occur, the mapping and the reducing. The output will be found on Hdfs, and from this, usually you copy back the data, the results, to your local storage, to your local home. So if we take the word count in MapReduce, so the word count is yes, the canonical example used to illustrate how the MapReduce programming model works. So the idea is to simply count the number of each word's appearance through a given set of input texts. So as I mentioned, there are two steps, the mapping step and the reducing step. So what does the mapper do? Well, one mapper, so one instance of the mapper program basically takes one line, one string of text as input, and it will just break it into words. Then it will just output the key value pairs, so each word plus the number of occurrence of this word in the string. And it will print that as output. The reducer, on the other hand, it will basically receive all the key value pairs that were output by the mapping step and actually made the global count of all the different occurrences. So if we take a look at the schema of the word count execution, we have an example with just a few sentences. So let's say we have as input just 3 strings. So the first one, the quick brown fox, then the fox ate the mouse, and now brown cow. Okay, the point is that each of those strings will be sent to the mapping step. Okay, so basically at the mapping step, you will see that the sentences will just be split. So here in this example, we have D that appears one time, brown one time, fox one time, and so on. So those will be the output of all the different mapping steps. Then you have a shuffle and sort step that I will explain a bit later on. And in fact, the output of those mapping steps serve as input for the reduce step, where the full count of the occurrences appear. And as you can see, you have in fact multiple reduce steps, instances, and in fact every single one of them will just take some part of the output. Thus we need a shuffle and sort step, which will basically order all the outputs of the map to properly direct the necessary output to the appropriate reducer. And then of course you will get the output, so basically the count, the global count of all the occurrences of each word. So here we'll try to keep the illustration as simple as just plainly through a terminal using plain commands without Hdfs, without directly map reduce. And so we'll just use input and outputs from std in to std out. And that's it. All the examples will run locally so that you can see exactly what's happening and how it works. So of course we'll need some material, and for this we also prepared something. So you just need to actually execute the first part of the notebook here. Yeah, of course, for me, those directories exist. Just wait a bit until it tells you that all the books are downloaded in the appropriate directory, as you can see here. Once this is done, there is another step here. We will also need this file. Just execute the box. It just prepares some of the material that is necessary to go forward. So I explained what the mapper was in the case of the word count example, and here we will try just to explain quickly what's in the code of this script. So here we create just one file with this content. As you can see, the first line is in fact just a way to tell Jupyter to create a file from the content of this sub notebook. That's what this is. Okay, so here you have the actual script for the mapper. So if we take a look, in fact, what happens is that for each line, it will receive from the standard input. It will first strip them, so basically remove the leading and trailing white spaces, if there are any. Then we will try to derive all the words, so basically split the line. And then we will just, for each word in the list, output directly to std out the word, a tabulation, then the value 1. So we're not actually here doing any count. Then in the reduce step, you see the count, the code is a bit longer, but the principle remains exactly the same. So the code is here. The first line is again just to be able to output the file directly to your terminal. So basically execute this box. You see it's creating the file. Same for the reducer. And in the reducer, if we examine the code, basically it's just a simple loop that will go through all the different information that were output by the mapper. So as you can see here, the input data comes from std in, so the standard input. Again, we do the stripping phase, so removal of the leading and trailing white space. Again, the data, so we print it using the convention word, tabulation, then the number, and here we just do the split in the same way. And then we will just basically count everything that comes in, okay? And once we are done with one particular word, we just print at the end the current word that was handled, again a tabulation, and then the total count for the particular word occurring. So if you take a look at how it will work directly through the terminal, here we'll just echo a single line of text, okay, with all those words. So fox, wolf, dog, wolf, whatever. And we will pipe it directly to Python to the mapper. And if we take a look at this, indeed, the output is plainly the list of the key value pairs derived from the execution of the mapper on this particular sentence. Okay, if now you want to do the full step, so the actual mapping and then reducing step, you just again pipe the results to the reducer. Okay, but as you can see here, we make the sort. So the point is that, sorry, all the key value pairs that are outputted from the mapper must be ordered, and here by key, okay, before being provided to the reducer. And if we try to execute this, then you have indeed the full count. Of course, you see there are some things that are maybe annoying, like cat that's counted twice, just because here we did not do any pre-processing. So of course, we did not remove the punctuation, we did not remove any special characters or anything. If you want to go further, you can actually try to implement this yourself in the place you think is most appropriate. Technically, it should be the mapper. You should do all the pre-processing there and then output the final key pairs at the end. So I hope everything goes fine until now. But I will maybe take a quick look at the questions if there are any. Apparently not. So here, the next one is an example a bit bigger. So in fact, in the first step, we downloaded quite a few books, and one of them is PG 20.417, and we will just take that file and pipe it again through the same way. So first pipe it to the mapper, make the sort, and then push it to the reducer. And if we do this, we get this result. No pre-processing involved, so the list is of course quite long, and some things may be considered totally unuseful, like for instance those numbers. This would depend on the actual pre-processing that you would like to apply on your particular application. Here the point is just to show you how the word count works with no pre-processing. Again, if you want to go forward, to go a bit further in this session, you can actually implement this by modifying the mapper and try a new execution. So now, this was just a purely local execution. The question now would be, okay, that was fine, but do I need to convert or modify this code in any way for this to actually run on an Hadoop infrastructure so that we can parallelize the execution of this program to maybe thousands of books? Well, in fact, no. There is a bit of work of preparation to be done, but no more than this. So what's this preparation work? Well, in fact, it's just pushing the actual files that are required to Hdfs. And when I say files, those are the books you want to analyze, but also the two executables, so the mapper and the reducer. So as you can see in this notebook, I first start by creating a directory on Hdfs, as you can see, to put actually all the content. Then here I make a copy from local. So basically I'm taking files from the local file system, so my home, to Hdfs in this specific subfolder. Okay. Then I will do that again, but for the executable, so the Python files. And of course, since this is behaving basically like any other Unix file system, you need to specify that those files are executable. If you do not do this step, of course, when the system, when Yarn, well, when MapReduce will, well, when Yarn will try to execute your MapReduce program, it will just say, okay, the permissions are not right. So basically, I'm just doing that, copying all the books to Hdfs, then copying all the executables to Hdfs as well, modifying the permissions appropriately, and then actually initiate the run. So the run can be initiated through this command. So it's a bit the equivalent of a slurm submit, an srun, an sbatch, something like that. Okay, but here it's yarn. So you have to invoke yarn, specify the jar file used for this operation. In this case, we are using just Python 3 is the one that is specified there. And then we have to specify quite a lot of things. We have to specify all different files that will be used in our software. So we specify first the file for the mapper, then specify that this is the particular file that is the actual mapper, do the same thing for the reducer, and also we need to provide the input and outputs. So as input, you will see that we just use path with a star at the end. We want it to actually ingest all the different books that are present in this directory. And as output, we just have to provide a path that points to a directory that does not exist yet, in which basically Yarn will be able to output all the different results. So if we try to execute this, okay, it mentions that the directory exists, it will push all the files, and then it will start the execution. You will see maybe the most annoying thing with Hadoop, with Yarn and so on, is the quantity of logs. Here it's still quite reasonable. You will see then that when reaching the Spark and Kafka session, this can be even a lot heavier. Here you can see that it runs through the mapping step. Then once the mapping step is over, it starts the reduce step. And once it's done, it will provide you quite a lot of statistics about the job. Just a few more seconds. Yeah, of course, keep in mind that, as I mentioned during my explanation before, the output directory must not exist before the execution of the program. That's the way it works. Okay. Okay, finally. So, as you can see, it provides you quite a lot of information about the actual job. So the number of bytes written, read, the number of operations, number of large operation, well, tons of statistics that can be useful at some point to actually debug huge softwares written in MapReduce. Here, it's not our main target. What interests us more is the way it stores the data. As you can see here, I asked a listing of all the files in the output directory, which is box output Python. And in it, I do a cat of the first file, which is part-00000. And as you can see, in fact, you have multiple of those files, okay? You have part 000 until 17. In fact, each and every single of those files actually represents the results of one of the reducer at the end. So basically, the mapper outputs all the different key value pairs, then this is passed to the reducer, and each of the reducer outputs to a file all the counts that it was able to establish. So technically, the full aggregation of all those files. Again, as I mentioned in the session just before, to actually merge all those things, you have the command get merge that allows you to retrieve all the content of this directory, merge it into a single file, and put it on your local home. But here it is. Here you basically have all the outputs of all the results of the reducing step in this particular directory, but under the form of multiple output files. So that's it for the word count in Python. Here, for the ones that are interested, you also have the exact same thing, but written in Java. It does the exact same operation. It just uses another language, another programming language to actually write the thing. So if you want to take a look at it, really go at it, take a look, fiddle with the code, do not hesitate. So if we make a quick wrap up, so we have seen basically in this session how to implement a simple word count program in MapReduce, so using this programming model. And we did it basically in Python to show it how easy it was possible to make it scale. So we first written it locally for local execution on one single machine, and then we transpose it directly in Python streaming, so in MapReduce on an Hadoop infrastructure for make it scale to whatever size of input file you may have. So fine, but as I mentioned earlier, there are there is one step, which is the shuffle and sort. Okay, in the examples before, when we did the execution locally, you saw that there was a sort between the output of the mapper and the input of the reducer. And in fact, this is it. This is what Hadoop actually does in the backend. So there is a shuffle phase, so which is a transfer of the map output from one mapper to one reducer in MapReduce, and the sort phase. So basically merging and sorting of map outputs. So the data from the mapper, so from all the mappers, are grouped by the key and automatically split among the reducers. So the point is that if you have, let's say, 100 mappers, and on each mapper you have one word that comes out all the time, like we would say D, T-H-E. Okay, well, in fact, this word will systematically, well, this pair of key value for this word will systematically be sent to the same reducer. That's what the shuffle and sort phase is for. So interestingly, shuffling can start before the end of the mapping phase. Okay, so one thing you can see quite often, in fact, when you start running jobs in MapReduce, are warnings about this will be displayed in the output of your program during the operation. You will see all the mapping operation, and at some point it will start to complain about a slow start. And in fact, it's just because it's not able to spawn soon enough reducers considering your software, and basically you are inducing a longer runtime for this, but it warns you about it, and you can make some things to avoid this issue too much. So technically, it's also possible to skip this shuffling and sorting phase, okay? In that case, what you need to do is actually to not specify any reducer. In that case, you are just using the mapping phase and doing all the required computation in this mapping phase. In that case, Hadoop, well, MapReduce won't try to make the shuffling and sorting, as it does not have to push the data forward to the reducers, okay? There is also a problem of partition. So technically, partitioning is yet another issue. So it determines to which reducer the output of a map phase will be sent. Okay, the default partitioner, which was used in the examples presented just before, uses hashing on the keys to make the distribution of the reduce task. So yes, technically it's possible to override this behavior, but again, this is like expert level. Do this when you know what to do and how it will actually improve the overall execution of your full MapReduce program. Okay, but usually for most of the small tasks, like for instance the word count, the default partitioner is quite fine. And so here you just have a schema that actually summarizes again all the different steps. So from the input to the splitting phase, to the actual mapping, the shuffling, the reducing, and then the final results. So if you have any questions, I will answer them, and then I propose to actually take a break of, let's say, 5 to 10 minutes, during which, if you want, you can, of course, modify the word count example that was provided here, like, for instance, to remove just all the special characters and punctuation in the text to get a cleaner output of the word count execution. Maybe just a quick comment. As you can see, well, as you have seen, the execution of my job was quite long. Okay, this was a bit surprising. I would have thought it would end up at least 1 to. But in any case, Hadoop is slow. Okay, you will maybe find this strange, but it's not. In fact, the problem is that here we are trying to execute on Hadoop a very small program using very small files. So as I said, Hdfs is not done for very small files. So the first thing is that this is not really adequate. It's just easy to show you and learn how this works. But also, since this is distributed, okay, this goes through Hdfs and of course Yarn, which is the scheduler. There are quite a lot of operations that occur beyond the scenes. Okay, so of course, when you try to execute some job that is in fact using very small amounts of data, the time taken by Yarn to actually spawn the job, package it, send it to the nodes, and so on, takes almost as much time as the computation itself. Okay, this is quite normal. If you were to use, instead of just megabytes of data like here, more like gigabytes of data, well, in fact, the time taken to spawn the job context would be, in fact, way smaller than the time to make the computations. Okay, so don't be scared by the fact that this seems slow. Yes, this is normal. This comes with a lot of overhead, but for big jobs, it makes sense. It needs to prepare a lot of things before sending it to the different nodes, make the coordination between all those things and stuff like that. So this is quite normal because this is not the perfect example. It's a perfect example to make you understand how MapReduce works. But technically, for such small things, you do not actually make an execution on a fully fledged Hadoop cluster because of this. Because the time required to spawn the job will technically be higher than the time it will go through the computations. Okay, but so be aware of, about this. It's technically quite normal. It seems a bit slow here. Also, something else before the pause, which I think is really essential. So we discussed Hdfs and about the way it replicates data among different nodes so that you have kind of a high level of resiliency and can lose one or even two copies or even more if you increase the replication factor replica before actually losing the availability of the data. You will technically never lose the data. So except if you actually kill and destroy a node and order Hdfs to destroy it, it's just that the data at some point won't be available anymore because no more replica will be available, but the data will still be there. When the nodes will come back online again, the data will still be there. It will appear again in the listing, be available and whatever. Yarn, in fact, does quite. Hdfs offers resiliency for the access to the object storage, so maintaining multiple copies of each file. But Yarn goes a tad further since it provides a layer of resiliency at the job execution level. So as you have seen, it was trying to spawn multiple mapper and multiple reducers. And in fact, those different units, those different small instances are distributed all among the different nodes available in the Hadoop cluster. Of course, you can also override those settings. So you can specify yourself a specific number of mapper you want or a specific number of reducer you want. But this is not even the most interesting thing. The most interesting thing is that if some node at some point dies, it's not an issue. It's just that this particular step of the task will just be considered dead by this scheduler and re-execute it on another node that is available. So except if you really have a catastrophic failure of the full cluster, just one dying node won't prevent your job to actually be executed until the end. Yes, you will have mention of those things. You will have errors in your logs mentioning the issue that occurred, but the program will get executed until the end of it. Every step that can fail will be restarted automatically by Yarn on another available nodes with the available resources and a node that is considered healthy. So that's one of the big plus of MapReduce, because as you can see, okay, the start, the creation of the software, the launch of the execution can take some time, but in fact, this is quite normal. This brings quite a lot of things in terms of resiliency for the execution of your job. So of course, this comes at a cost, the cost of the preparation of all the context and the launch of this necessary context. So I hope you were able to actually use the notebook and make a few tests. Now we will continue with the Spark session. So quick recap. So the Hadoop framework is based on a simple programming model, which is called MapReduce, as we've seen. And using it, we can make computations that are scalable, use basically multiple machines for a single job, fault tolerant, because as I explained, if your job is sent to Yarn, and it's written in MapReduce, multiple units that will be executed on different nodes, and Yarn will take care of restarting the step that failed at some point because of a node crash or whatever. And it's also cost effective. And this is for multiple reasons. First, because having multiple machines are usually less expensive than having high density servers with high core counts and something like this. but also because it can run on very heterogeneous hardware. So basically, you can actually install a full Hadoop stack on any types of machines. You can mix them together. You do not need to have symmetry in any way, like we would say the same number of cores for each machine, the same amount of storage for each machine, or even the same amount of memory on each machine. Hadoop takes care of all those things. So technically, you can even push and keep working with older nodes and integrate them in a new structure. It's really not an issue. Basically, the Hadoop framework handles all those things, which is quite nice. So for Spark, technically it is not an alternative to Hadoop. It just depends on it. Okay, so Spark uses Hadoop for storage, so it uses Hdfs, but also Yarn to make the actual reservation. As we've seen, MapReduce is just a programming model. When we write a program like this, we submit our job through Yarn. So it's indeed Yarn that handles the scheduling. So Spark, in fact, runs a bit in the same way. It uses Hdfs for data storage, and it uses Yarn to actually make reservations for resources. So Spark is designed to make fast computations. It extends the MapReduce model to other types of computation, which include interactive queries, as well as stream processing, machine learning, SQL queries, graph algorithm, and really much more, because this is evolving still quite fast. So in Spark, you have multiple components that are quickly described here. So you have the Spark core, which is basically the underlying general execution engine for Spark. Spark SQL, which is a component built upon Spark core that introduces data abstraction mechanisms called schema RDD. We refer to them usually as just plain RDD, that provides support for structured and semi-structured data. Then you have Spark streaming. Basically, as its name indicates, it just allows you to do stream processing, then MLlib, which is oriented towards machine learning, then graphics, oriented towards the manipulation of graphs. So now, let's go back to our operations in MapReduce. The main feature in Spark is, in fact, the following. It's in-memory cluster computing. The question here is, why is this important? We've seen something in MapReduce. Okay, it was a bit slow start, but the point is that it offers resiliency. But why maybe is it slow? Why was it that slow? Because indeed, handling all the books that you've seen in 3 minutes, you may find this technically slow. Okay, but there is a reason for that. MapReduce is quite convenient because it allows users to write parallel computations without having to worry about the way the work distribution must take place, and it also handles fault tolerance, as I just explained. However, the real issue in MapReduce is that the only way to reuse data between computations is to actually write them to Hdfs. So if we take an example here, okay, and we just consider really just the mapping and reducing step. So consider that iteration 1 is the mapping step and iteration 2 is the reducing step. What happens is that first you need to push data from your local home to Hdfs, okay? Well, that is required at some point anyway. But once you start the MapReduce program, what happens is that it will actually read all the data. Okay, split them among the mappers. The mapper will output information, but it will not be piped directly to the reducer. No, the data will be written to Hdfs, then reread again to feed the reducers, and then Hdfs will be used again to write the data of the, well, basically the result, so the output of the reducer. So you see that this involves, in fact, quite a lot of read and write operation directly on Hdfs. So I wouldn't say that it's slow, it just involves a lot of operation on disks, okay? Because also one thing that is quite nice in Hdfs is that is the idea of data locality. So the point is that the best it can, it will try to push the necessary computations to the node that actually has a copy of the data. So it will try to avoid moving data through the network. So it's really nice, but still, it's a lot of read and write operations. Okay. So the main difference with Spark is that it will try to avoid that. It will try to avoid writing to disks for each and every single step. So, as explained briefly, sharing data is slow into the canonical MapReduce paradigm, so what I just explained. The real problem is that, in fact, most Hadoop applications spend 90% of the time doing Hdfs read and writes. That's the issue, and that's technically the issue we've seen in the execution of my program. As I said, it was a bit whatever, but nonetheless, most of the time is used first to generate the context and start the distribution of the workload, and then it's reading, computing, writing, rereading, computing, and rewriting. So it does that quite a lot of its time. On the other side, Spark uses the RDD, so the resilient distributed dataset that support in-memory processing computations. So the idea is just to store the state of memory as an object across the jobs, and this object is simply shared between those jobs. So the point is that instead of having Hdfs as a common location to store new information, basically you will have kind of the same thing, but with an abstraction, and the data will be stored in RAM all the time. And so if we take back the schema we've seen previously, where I showed when basically we were reading data from disk and writing data to disk, we see that this is here quite different. The point is that we will start reading the data from Hdfs, because of course the data is initially in Hdfs, but let's say, for instance, it would be a MapReduce execution. Well, between the mapping and the reducing step, the data wouldn't be written to Hdfs, but would be written to memory and read again directly from memory. Again, of course, Spark requires the start of some context. So the launch of the job will still take some time, but we won't lose the time required to read and write information between the different iterations. So, in a sense, all intermediate results are stored in RDD instead of files on disks. But, of course, if the amount of memory available or actually reserved for your job is not enough to keep all the information in RAM, well, it will then dump the information in excess directly to Hdfs. So to be able to really gain everything you can from using Spark for, in this case, I'm just making a direct comparison to MapReduce. So just to improve the way one software written in MapReduce would run, the point would be to actually calibrate the amount of memory you need so that the disk, well, Hdfs, is not used during those operations. But clearly, if at some point it needs to go higher, maybe because your reservation was not enough, there was plainly not enough memory when you wanted to execute your job or whatever, it will be able to do it, but it will write again on Hdfs. Also, be aware that by default, each resilient dataset run an action on it. You may persist an RDD in memory for fast access or on disk, or even replicate it across multiple nodes. Depending on your use case, as well as the amount of memory you have, you may or may not be able to access. You may have to use one of those possibilities. So basically, depending on the data you want, you plan on manipulating, you need to be able to make either the appropriate reservation in terms of memory, calibrate your job so that it will run exclusively in memory. It's just a fail-safe, so if you fail, in fact, in this step, it's not an issue. Spark will continue to run, no issues at all, but it will write on Hdfs and you will see a drop in performance, which is quite logical. So now, let's take an example here. So again, the word count, but written in Spark. So here you have basically a quick example of the actual software that we could execute. So you see that we import a few libraries, we try to derive our username, and the app name we will provide, because of course we need to be able to locate this job, like it's not a job identified by a random identifier. Here we just define ourselves the name of the job. We need then to start a Spark context, and here you see we mention local. So in fact, the point is that when you try to run a job using Spark, you can execute it in two ways. So either locally or using yarn. So here we just do it locally for this to be a bit faster. But this means that it will try to make all the reservation of memory directly on the Spark node. If you use the yarn assignment, in that case, it will actually use memory provided by the workers handled by yarn. That's the idea. So we initiate the Spark context. Then we need to specify one text file. So here, in this case, one book. And so we declare it basically and specify where it's located in Hdfs. So Hdfs // the actual node we want to contact and on which we want, through which we want to locate the file. Then what we do is the actual full operation. So we do a flat map, the split using lambda programming, the reduce by key, and so on. And then once we have the counts, so the information we want at the end, we just save this information on a file, again, on Hdfs. So here it will be in /user/username/appname _ testing single. Okay. So then if we take results of this, we see that the job was successful and you have one file, part 0000, with all the different pair found in this book. And as you have seen, it's quite fast this time. And why is it that fast compared to the previous example? Well, for two reasons. The first one is that we're not using Spark using yarn, but just locally, but also because basically we are running everything in memory. So all the intermediate results were stored in memory instead of written and read again from Hdfs. So technically, if you use an initiation of the Spark context using yarn to have the resiliency and more nodes to reach to get more memory, in that case, of course, the startup of the job would take a bit longer, of course, to make the reservation of the resources and so on. But so that's the idea. That's a plain, simple example of the equivalent of the word count, but written in Spark this time. So now, let's imagine that, because this time we just processed one file, let's imagine that you want to handle just multiple files. Well, in fact, the only thing that will change will be the path. In this case, you won't provide, like in the plain MapReduce in Python streaming, you will just specify the directory. Here, not. You just have to specify all the files. So here, star.txt, it will take all the files in the folder that are actually books and run this again. So let's run execution. Done. You see how fast this is. Again, it's because it's executed locally on Spark, so it does not generate a yarn context here. It's just for the purpose of the course. But nonetheless, no operation in between the mapping and the reducing step, so it runs really, really, really fast. Again, we can take a look at the results. You see here in this case, you have, of course, multiple parts because you have way more information that was processed by Spark. So the results are split in multiple files. And again, the output of the key value pairs. So now the Rdd operations, because here you have seen that basically we made, we called some lambda, we made some splits, we made a map, a reduce by key. Okay, all those things are in fact Rdd operations. So you have technically two types of operations, so transformations and actions you can use in Spark. So transformations and actions are two types of Rdd operations that you can conduct. A transformation is just a function that will produce one or multiple new Rdd. However, it's possible to actually work with the loaded data set using actions. So why creating new RDDs each time? Well, because RDDs are immutable. Okay, you need to keep that in mind. It is important to notice that transformations are not executed immediately, but only when we call an action on them. Okay, that's a quite common error when we start working with Spark. We try to invoke something and we are weirded out because we do not see the actual results, but it's quite logical. It's just because of this. So there are two types of transformations. First, the narrow. So in those, all the elements required to compute the records in a single partition live in the single partition of the parent RDD. In this case, just a subset of the partition is used to compute the actual results. And for instance, in the narrow transformations that you can use are map, flat map, map partition, union, filter, and so on. Then you have also the wide transformation. And in this case, the records are computed for a single partition, maybe in many partitions of the partition of the parent RDD. So let's, for instance, take group by key, reduce by key, distinct, intersection, join, Cartesian, repartition, coalesce, and so on. And here you have a depiction of the difference between a narrow transformation and a wide transformation. It's maybe way clearer than just the textual description. As you can see, in narrow transformation, you go from one partition to another one, but using just the initial partition, where in fact in wide you are able to go among multiple one of them. So here in the next notebook, you have the data set, so just execute this. It will basically create the file required to test the different operation. Then you need to copy this file using the following notebook to Hdfs, and then you need to create the text file in the Spark context so that you can manipulate it. Then you have multiple examples: the map, the flat map, the reduce, the filter, map value, flat map value, and also some other actions. So for this, honestly, I don't think it would be really interesting for me to go through the description of all those simple operations. It's way clearer for the returns I had in different courses for you to actually test those things to see how they behave. So here I will just plainly execute those and then leave you, let's say, 15 to 20 minutes to actually test all those different operations and see how how the output looks and how basically this works. Okay, I think for you to see that, yep, I will just execute them all just to confirm everything is okay and runs fine. And as you can see, this goes quite fast. Of course, we are running everything in memory, direct memory access. We're not going through Hdfs or whatever. So of course, this part of the session is way more interactive. So really do not hesitate, test all those things, fiddle with them and see what's what. For the ones that are already familiar with Lambda programming, this should be quite easy. For the other ones, do not hesitate to actually go inside every single notebook and break every single one of them to be able to be sure to understand perfectly every single operation and how they work. But that's it for this session. I will leave you to it. Take a look at it, use the different operations, see their output, verify they do correspond to what you expect, and then we'll proceed forward with Kafka. Yes, indeed. So I've just received one remark concerning the different names. Indeed, I did not even realize this. But let's take, for instance, the ones that you have on screen right now. You have Hadoop, FS, LS, user, then M Waumans. Well, this is supposed to be my login. So feel free to leave it this way. This won't prevent the notebook to work properly, but technically the line should be different and should look something like this, or anything you would want to actually use. Okay, so it's not an issue, but well, be aware that normally your username could be used here. It does not have anything to do with my actual account. It's just a plain directory name that was used here. So I hope you were able to actually test some things with this notebook and get a better grasp at how map, flat map, map partition, and all these different other operations, either narrow or wide, do work. But I propose to continue with the Kafka session. Then quickly discuss about Spark streaming, but really just quickly, we won't have the hands-on part on it, even though you will have example on how this works. And then for the ones that desire to do so, they will be able to still continue to use those notebooks for the end of the sessions without issue, to go back to the things that are maybe interesting the most for them. So let's go through Kafka. So Kafka is a distributed streaming platform. So Technically, the term big data most often implies the manipulation of large amount of information and not specifically just huge files stored somewhere. So this leads to multiple challenges, among which you have, of course, data collection and then data analysis. With Hdfs, we have means of storing the actual information in large quantities, and with MapReduce, we have at least one way, because it's just one way of making data analysis over those. However, the problem of data storage and data collection are totally different. So as I said, data storage, we have this. We have something that is distributed, replicated, resilient, whatever. But this is just for static files. If you actually want to be able to ingest data, maybe continuously, you need something else. So Kafka tries to answer this, or at least propose one solution for this problem. And what's Kafka? Well, it's a messaging system designed for high throughput distributed systems, able to actually ingest large amounts of information that would be generated as a continuous flow by whatever system. And it offers also better throughput than other messaging system. It also offers replication, also fault tolerance, and it's built in with partitioning, and as such, it's quite a good candidate for large-scale message processing applications. So the point is that Kafka is just installed next to Hdfs and everything else on the different nodes. And so basically, again, it's built for resiliency. So if one node dies, it's not an issue. If one node dies, you won't lose all the information because either the information is in memory or it's directly consumed through Hdfs. So in any case, the system completely is built around the idea of having fault tolerance. So I said it was a messaging system. Okay, but what is this? So the first question to ask here is, did you ever already use maybe MQTT, for instance? The point is that MQTT is quite similar. It's just that Kafka pushes the idea way further. So the idea behind search system is just to transfer data from one application to another. So basically, you will push from one application information through Kafka, and any other system will be able to actually consume this information from Kafka, either live or either maybe going back in time to actually consume the data from the start of the production. So yeah, of course, you have multiple types of messaging systems. So the first one is the point-to-point messaging system, and in such, all the messages are persisted in a queue and can be consumed by multiple consumers, even though a particular message in the queue can only be consumed by one user only. So in a sense, once the message in the queue is read by a consumer, this message is removed from the queue. Okay, so you are able to technically go back in time, but with Kafka, but here, for instance, technically once the message is read, it's supposed to be out of the queue. Then you have the publish subscribe message system. So here the key characteristic is that all the messages are persisted in a topic. It's in what we call the topic. So basically, if you want to create a queue, you will create a topic and you will provide information in this topic or consume the information for this topic. Here, consumers can subscribe to one or multiple topics and then can consume all the messages in those particular topic. Okay, so the point is that in point-to-point, when a message is read, it's out of the queue, it disappears from it, but in publish, subscribe, multiple applications, multiple users can consume the same topic. Everything is persisted, so that indeed you can possibly go back in time and reconsume everything in the queue. So now the question would be, okay, why to use Kafka? So as I mentioned, it's the distributed system. It's a distributed publish subscribe message system, which is focused on high throughput. So all messages ingested by Kafka are persisted on disk, so on Hdfs, and are also replicated within a given cluster to guarantee fault tolerance and thus prevent data loss. However, Kafka relies on also another service, which is Zookeeper, which offers Kafka the synchronization information it needs to run properly in a distributed way. I mentioned this in the first session, I think, mentioning that Zookeeper was on the side next to Hdfs, Yarn, and so on. In fact, it allows all the different systems to be coordinated and to have a single point to store and maintain all the configuration, and thus possibly also the synchronization between some of the services. So what are the benefits of Kafka? Well, first, reliability, since it's distributed and replicated and offers fault tolerance. Scalability, because technically we can add any number of Kafka nodes as long as we have enough resources. Durability, as all messages are persisted on disk. So you have kind of an history, like I was saying just before. And also performance. It's really designed for high throughput. So what can you use Kafka for? Well, there are multiple examples. Those are just examples. You can technically make whatever you want from Kafka if it fits your needs. But the most common usage are for log aggregation, metrics, technically metrics aggregation as well, and stream processing. And that's what we want to talk about. So there are frameworks like Storm and Spark Streaming that can actually take advantage of Kafka to process information in streaming fashion and even possibly in real time, thus offering us different means of making data analysis. In fact, in MapReduce, you only do batch processing. So as you've seen during the example, it's quite representative of the thing. You prepare software, you execute it, and once the execution is done, it's done. The program stops. So if you want an execution to occur multiple times or maybe constantly, you are forced to actually just rerun and rerun again and again your software. You cannot handle continuous influx of information without having to invest quite a lot of time, in fact, in automating your submissions. And also it's quite inefficient. Basically, do not try to do that. As you've seen, job in MapReduce using yarn takes time because it needs to generate the context each time you submit a job. But with Spark, basically you have this overhead to create the context, create the job, but then once the job is there. Okay, it will stay there until the end of the execution of the streaming context. So this makes it capable of actually handling continuous influx of data without all this overhead of starting and starting again softwares. So you have multiple concepts behind Kafka. So you have the Kafka standalone, which is the actual instance of Kafka using a single broker. So technically you can use Kafka standalone. It's just not providing you anything in terms of high availability. In that case, a Kafka cluster, so multiple Kafka brokers put together and coordinated. Topics, which are a stream of messages from a particular category. Those topics are split into partition that store messages in an immutable ordered sequence. Again, immutable. We are storing data in Hdfs. The point is not to do read-write, just keeps a history of all messages that came in. The partition offset, which is the unique sequence identifier. So basically it's the position in the queue that you are consuming. The replicas of a partition are exact copies of the partition. So again, it's based on Hdfs. So the point is that everything is written to Hdfs and you have multiple copies of all those things. Then you have brokers, those are the simplest system responsible for maintaining the published data. So in fact, for each Kafka node, you have one broker running on it. Then you have the producers, so the one that actually take a topic and push messages, push data in it, consumers, the one that actually take a topic and try to read information from it. Then the leader, which is in fact the leader node responsible for all read and writes for a given partition. Thus each partition has one server acting as leader, and then a follower node, which just follows the leader's instruction, either replication or takeover or whatever. And of course, for the coordination of all those things, we do not forget Zookeeper because it's because of this system that it's able to do this. Kafka does not handle all the things by itself. So we'll first start with using Kafka from the command line, plainly. So I'm a bit sorry, but there are already multiple topics existing, so I have to go a bit through the logs each time to show you what needs to be shown, but instance for this. So here we have a first example, a first plain command that you can of course execute in the terminal, which is Kafka topics dash list dash zookeeper public 00:12181. What is this? Basically, what you are asking here is that you want Kafka to provide you a list, and to be able to provide you this list, you need to provide this specific command of Kafka, the Zookeeper instance, or at least one node of the Zookeeper instance. And in this case, Zookeeper resides on the node public 00 and is accessible through port 2181. So if we try to execute this up, you see that Kafka is quite a bit verbose, but yeah, let's go through it. You will see at the end all the different topics. You see here SESI, all the different SESI accounts that are from previous executions and so on. You see multiple ones, then also one which is technically mine. So just for this to work properly and in order, I have to remove mine. Up. Let's go here. So this was just the command to list all the existing topics in Kafka, so all the topics that are available to be consumed. So reading those names, you will of course say, okay, but that's weird. You're Waumans, you shouldn't be able to see all the other topics. Well, in the way this is set up right now, yes, there is no RBAC, so it's not possible. So role-based access control. So basically everyone can actually access those things. However, of course, it's possible to make and place restrictions on those access. So don't worry, this is normal, it's the way this is set up. If you want more security, there are a lot of things that you can do to get it out of an Hadoop stack. So now, if we want to create a topic, the command is as follows. So again, you call Kafka topics, you tell it to create a topic, you have to specify the Zookeeper instance that is responsible of your Kafka cluster. You must specify the replication factor of the topic. So either one, in that case, you have a single copy and not the resiliency that you would like to have. So in this case, we select 3. So the usual thing that we use generally when on Hadoop. Then the number of partitions. So basically the number of splits that will occur to actually store your data. Here we use 5. It's technically possible to tweak this, but this really depends on the workload that you will put on it. So there is no magic number to be used. Then the name of the topic that you want to create. So once you execute this command, it will specify all the different libraries that intervened in the creation of topic, and if you go low enough, you will see here created topic Waumans. Then again, if you want to confirm that the topic was properly created, you make again a new listing and you will find it again below. If you want to remove it, same thing, you have a command line to do specifically that. Up. It will mention you that a bit later on. Okay. Here you see the topic is marked for deletion. Now, if we want to start a producer, because here we just saw the way to list the topics that are available, to actually create or delete it. But now if we want to create a producer, so basically a topic that will be able to produce data. So here what we do is that we call the command Kafka console producer, which allows you to actually start a producer just from plain command line and not a software that you would have written. You have to specify the broker list, so basically the nodes that you want to contact to make this operation. And here, those are the nodes of Kafka, the Kafka nodes explicitly. So in this case, we take one of them, so public 01, which is accessible through port 1992. So yes, it's a bit heavy. You have to specify all those things systematically, but technically it's to provide you better control over what you do with this distributed structure. Then you specify the topic on which you want that you want to be filled with information. And what you do is just that you ingest data from the book PG 20417. Okay, so technically when you launch this command, what will happen is that it will basically execute the job. And as you can see here, it's not really readable because of Jupyter. I'm sorry, it's quite convenient to show you stuff, but at the same time, sometimes the logs are a bit weird. So do not worry about this. It started the producer, and now if you want to be able to consume this, you will call Kafka console consumer. Again, specify the bootstrap server on which you want to be able to start consuming the information. So we specified exact same node, so public 01, the topic we want to consume, and we specify explicitly that we want to consume everything from the beginning. Okay, so technically, if you started already to consume it, you would reach a certain index, okay, from which a certain word in Kafka, and so technically, when you will want to start again consuming, if we do not specify from beginning, it will start back from this particular index, from this particular offset. But here we specify explicitly we want to read everything. You execute this and up. And you see that the full book is being read from the topic. Okay, so in this case, it's really just a plain example on how to actually use this from command line. So it's convenient, but usually it's really more interesting to be able to integrate this in your particular software. However, it's important nonetheless to be able to see how this runs just plainly from a terminal. So you have also the possibility to describe a topic. So if we execute this on mine, it will provide us, I will have to reset. So if you wonder why I reset this, it's because technically the consumer will continue to push forward when technically it's not necessary anymore to continue. So here, if I take describing a topic, again, Kafka is a bit verbose, sorry for that. But at the end, you will have the description of the topic. So you see the topic is named Waumans, the partition count here is 1, the replication factor here is 1. Then you have the config, the leader, the position, the offset, and so on. Okay, so at every single moment you are able to describe a particular topic, where it's at, how it was consumed, at which step is it, and stuff like that. If you want to consume a topic not from the beginning, but a specific offset, you just have to specify it again. So just before we wanted to start from the beginning, but you are able to start directly at a specific given offset if you know which one. Now, this was just using a single node. If you want to be able to use the same thing, so create topics, list topics, create producers, create consumers, in cluster mode, basically you just have to provide all the different nodes from Kafka. So here in the broker list, you see that it's not a single node, you have multiple ones. That's the only difference. You just have to specify all the nodes that you want to be involved in the topic. And that's it. So now let's get out of the command line because it's nice, but again, not really convenient for many things. The most interesting thing is to actually embed this in some code, and here in some Python code. So let's say you want to actually produce information through Python, okay? Wait just a minute so that I'm aligned. Yeah, to avoid having too many informations in this, I will just do that and do that. Here it is. So here you have a quick examples on how to actually use Kafka through Python. So here we just, again, take our username to be able to create a topic using that particular name. Then you just invoke Kafka producer and specify all servers involved in the cluster. So here the nodes public 1 to public 5. Okay, and then you just have to send information. So you tell the producer to send to the topic that we want to use this message, then this message, then this message. Okay, that's it. And now if you want to be able to consume it, in that case, you won't call Kafka producer, but you will call Kafka consumer. You specify the bootstrap server, one or multiple ones of them. It's of course better to specify multiple ones when you have them, because this way you gain resiliency. You have, of course, multiple parameters you can use, but then you start just consuming the queue and print all the different message from this topic. So the topic, the partition, the key, the value, and so on. And that's it. You have the output. So the topic, the partition, the key, and then the message. Because in this case, I just send plain strings, so I do not have the other part. But so that's it. You see how simple it is to actually take advantage of Kafka to be able to produce messages, to produce information in a streaming fashion, and being able to actually consume this information still in a streaming fashion, just plainly using Python. There is tons of information and tons of examples on the web, like this one, that can be more complex usually than the one that is proposed here. But at least you see how easy it is to be able to take advantage of such system that is clearly the best thing to use for a real-time application where you want to be able to consume data continuously. So here it is for Kafka. So if you have questions, do not hesitate. Oh yeah, so for the error that is in the chat, so the error that says cannot run multiple Spark contexts at once. So yes, you cannot indeed do that. So the point is that, quick explanation, if you were inside the terminal, you would start Spark and reach basically a console like, well, you would start PSpark to be more precise, and you would be in a console like Python. Okay, no difference. The point is that once you are done with it, usually you will just exit it. In Python, what happens is that when you run the first part here, sorry, let me, yep. If I was in the good one, that would be better. If you take a look at this first block of code, in fact, it's here that we do initiate the context. Okay, the point is that once the context is initiated, you're supposed to continue to run with it. So if you execute this notebook twice, it will just tell you, no, you cannot create another context. So if you want to get rid of this error, in fact, just restart and clear output. Well, I will maybe just try to show you the issue. Yeah, you see, that's the error that was mentioned. Okay, cannot run multiple Spark contexts at once. In that case, kernel, restart, and clear, go back in the box and execute it again. Now the Spark context is ready and you can execute all the different, yeah, not the same error, sorry. But of course, since I'm trying to run the job using the same directory that already exists, it spawns me another error. But so if you have the error cannot run multiple Spark contexts at once, you do kernel, restart and clear outputs, re-execute this notebook and proceed forward with the notebooks that do follow. Okay? You really have to take this like you would execute Python in a terminal. Once you have started a few things, technically all those things are still in memory in the context of your execution. It's just that the Spark context cannot be initiated multiple times. You need to initiate it and then continue to use it, or you have to destroy it and recreate a new one. So here, to make things simpler and quite quicker, since the examples are quite small and simple, do a plain restart and clear output of the notebook, and that's it. No other questions right now? Then I will proceed forward with a quick explanation of Spark streaming and how to use it. I won't be able to produce any running example of it because of a dependency problem of one library. I'm sorry for this, but this is specific to the version we are running of the full Cloudera stack. So basically one library is there, but it doesn't want to use it. So I still need to upgrade this. This will be available in version 2, but nonetheless, the codes that are provided in this session are running or working perfectly fine. So once the cluster will be upgraded, you will be able to run them. But so Spark streaming, because we've seen right now, well, in the previous session, just how to use Spark, what were the operations possible, what were RDDs, how it was way faster than MapReduce because running directly from memory and so on. But we also mentioned the Spark streaming thing, which is basically a part of Spark. It's just something that relies on the other building blocks of Spark. So the streaming aspect here implies that Spark streaming allows the processing of unbounded data sets. So instead of processing well-defined batches like what we did in MapReduce or even what we did in Spark in the examples provided before of data, this approach allows you to handle continuous influx of information. So Spark streaming is a framework that natively supports processing within batch and across batch. Okay. However, are you forced to use something like Kafka? No, you can do it using Hdfs. If Hdfs is not fast enough, would Kafka be a better solution? Yes, maybe. Technically, Spark is capable, when you write something in Spark streaming, is capable of ingesting data from almost any source you want. It's just that the two simplest examples are consuming data from Hdfs directly or consuming data from Kafka. It's one of the simplest examples, but it's also a use case that is very, very, very common. But be aware that you could consume data from elsewhere. It's really not an issue. So how does this work? Well, in essence, Spark streaming just receives input data streams from any types of service, like I said, and divides them into batches. Those mini batches are then processed by Spark in batches. Why this division in batches? Well, in fact, it's just to parallelize the processing across as many machines as we are allowed to use in our reservation of resources. So in fact, Spark streaming just provides a high level of abstraction to manipulate those influx of data. So these streams can be created from an input source like Kafka, for instance, but not only. So the D streams, what is this? Well, the basic abstraction provided by Spark streaming. A D stream is represented by a continuous series of RDDs, and each RDD is a D stream. In a D stream, contains data from a specific interval. Okay, so any operation that is applied on a D stream translates to operations on the underlying RDD. If we consider a simple example where the stream of data is a stream of line of words, so simple sentence, a simple string of text, like just what we manipulated during the other sessions. A flat map operation is applied on each RDD in the lines to generate as output the words. This stream thus contains a list of the words present in the processed sentence, and that's it. So for streaming data, you have basically two options. So use basic source, okay, which for instance can be a retrieval from a file system. And you will see that it's really, really easy. Or use an advanced source like Kafka. But technically, you are not limited to Kafka. And repeat it again, you can use other alternatives. However, do not forget a few things. Once a context is started, no new streaming computation can be set up or added to it. So it's like you create a program that is capable of handling streaming data and making computation on the stream of data, but you cannot adapt it live. Okay, once a context has been stopped, it cannot be restarted. Yes, you can re-execute it, but you cannot just pause it and restart, basically. A single streaming context can be active in a Java virtual machine at a time. And the function, just explaining the error we've just seen. And the function called stop on the streaming context also stop the Spark context. So it's a full stop. However, you can only stop the first one by adding the parameter stop Spark context set to false, if you wish to do so. Those few remarks are in fact very important when debugging, when taking Spark in your hands, because you will try to write a program, say, okay, it seems fine, I'll run it, then I run it again, errors, run it again, errors. Usually those are due to those main points. That's why they are written down there, so that you have something to get looking all through the Spark documentation, because those are the most common error and mistakes that can occur. So again, let's go back to the word count, but this time in a streaming context using Spark streaming. So you won't be able to execute those. As I mentioned, there's an error of dependency, at least not the ones related to Kafka, but for the others, yeah. So so here you will be required to create your Python executables from the command line interface and execute them locally by invoking your script from the command line. Okay, so the next question that comes usually here is this the only way of submitting PSpark jobs? No, there are multiple options. So technically you can either start PySpark2 from command line and then write your script interactively like you would do in Python. You may also start a Python script that use PySpark libraries from the command line, or you may submit a Python script to Spark submit from the command line. So technically you have three ways of actually doing this. Another thing, will all methods work out of the box? They should, but yeah, no, they don't. The issue here is very simple. Spark is written in Scala, but you can use its core from either Scala, Java, or Python, which implies basically multiple layers of software dependencies. And technically, that's the issue I have, and that prevents me from showing you the whole things working live. On top of that, a Spark submission under Yarn supervision implies that those dependencies must be met on all the different machines implicated in the job processing, and that Yarn's own dependencies are met. So basically everything needs to be tip-top everywhere. But usually the most annoying issues are like the one that I have right now, and it's just a plain question of dependency of libraries around Spark and then the system you want to use to be able to ingest information. If there is a difference there, you may have issues. That's the case in this context. And also, indeed, take great care. If you install software on a structure that you may have installed yourself, all the different workers, all the different nodes under Yarn's supervision must be perfectly identical in terms of configuration, because indeed, it's not, let's say you submit your job, all the dependencies are not inside your job. There may be dependencies between Spark streaming and Kafka, for instance, which is exactly the issue we have here on all the different nodes. It doesn't depend on your own software, it depends really on the configuration of the different nodes. So it's really something quite complex to maintain an Hadoop infrastructure. You can gain a lot from it, but it can be quite complex. Also, quick tip for the ones that want to use Spark or Spark streaming. There is a library. So the issue is so great that there is even a library that you can install, which is called FindSpark, that will actually try to locate the exact position of Spark among the tons of jar files, so the tons of libraries installed in your Hadoop environment. So it's that bad. It's really annoying. Once it's done, once it's set up, it's perfectly fine. So whenever you use an Hadoop infrastructure, read the docs to the end. Those informations will be provided, and really debugging this step by step is really annoying. So better read the documentation first, then go forward. So here, we'll just show you a quick example of word count from the local file system. So as said, there are multiple ways of actually creating a job or running in Spark streaming. You can consume data either from disk or from Kafka. So the example that works here perfectly fine is the one that consumes data from Hdfs. So how does this work? Well, here you have an excerpt of code in Python that runs perfectly fine. So basically it includes the creation of the Spark context. We just name the program reading files from a directory, which is exactly what we will do. We create, because we need to create a streaming context, and we specify the text file stream. And as you can see here, the path is ./sesicourse/bookstream. So it's not a file, it's a directory, okay? So the point is that once this is defined, you just specify the operations to be done. So here, the split, each line into words, the count, each word in each batch, and so on until the end. What will happen, in fact, if you do this? Well, let's execute that. It will start, run, no issues. And the point is, you see, it will say, okay, here is this timestamp, here is the next iteration that occurred. Nothing appeared in this particular directory. And that's the idea. Once initiated this way, the Spark streaming context will examine this particular directory non-stop in search of a new insertion, in search of a new file. So here, let's copy something in there. Here it is. Sorry, took me some time, but yeah, apparently there is an issue with this line. Apparently the paths are wrong. But so basically here what you see is that, whoops, sorry. It's a bit difficult to navigate through that. Yeah, so at some point what happened is that Spark streaming saw that a new file appeared in the directory. So it loaded that file, it processed it according to what was specified in the software. So here, the map, the reduce by key, and then the print. And that's basically what you see here. You just see an excerpt, but that's the idea. So that's the simplest way to actually make a streaming context that ingests data directly from your file system, which is quite convenient. So in this example, just keep in mind that these examples read information directly from the local file system and not even Hdfs. If you want to run it through Hdfs, you just have to specify another path. So as you see here, you just create a text file stream, but instead of just locating the file in your local file system, you have to specify the address on Hdfs. So basically Hdfs // the address of the master node and then the exact path. And Spark will run exactly the same way. So you will be able to feed data in Hdfs, and especially if this is if those are huge volumes, and the Spark streaming context will just read. That's it. It's really as simple as that. Now for the latest one, so the ones that technically do not work here, it's the word count from Kafka. So in fact, the issue resides with this, so that you know, okay? This is the issue. Even though the library required to make Spark streaming run with Kafka is not accepted, even though it's right. So that's the issue. The rest of the code, though, is perfectly correct. So if you take a look, you just create a streaming context exactly like in the two other examples. And here, what you are supposed to be able to do is just call Kafka utils, create a stream, you specify the Spark streaming context, you specify the broker that we defined just here, and then you say, okay, I want to consume the topic number 1. Then what will happen is that it will just consume continuously any flux of information that comes in this particular topic. So, of course, you are able to tell your Spark streaming context to stream everything back from the start. Okay, when you, let's say, restart it after a complete modification, a complete overhaul of the code, you can start again the consumption from the beginning. But if you do not specifically ask for that, what will happen is that it will just continue to consume new messages that arrived in Kafka from the latest offset that was present. So that's it. So keep in mind, this example is not executable in this state. It will just bring you errors about the fact that the library for Spark streaming with Kafka is not present, but the code is exactly the one that you should have. besides the import of the library. And the two other examples just show you how to use your local file system or Hdfs to be able to consume data continuously and create streaming context using Spark. So yeah, we reached the end of this session. So I hope this was interesting for you. I'm sorry for any quirks and things a bit maybe peculiar with this session, but as I said, this is the first time I do this fully live. I must say this is a completely different exercise than the usual. So I hope it was still interesting to you. I will leave the accounts available for the day. So if you want to continue going through the different notebooks, feel free to do it. But after tomorrow, those accounts will be disabled. So here it is. Thank you for your attention, and I hope this will be interesting for you.